Electromagnetic radiation, Wikipedia audio. In physics, electromagnetic radiation refers to the waves of the electromagnetic field, propagating through space-time, carrying electromagnetic radiant energy. It includes radio waves, microwaves, infrared, light, ultraviolet, X-rays, and gamma rays. Classically, electromagnetic radiation consists of electromagnetic waves, which are synchronized oscillations of electric and magnetic fields that propagate at the speed of light through a vacuum. The oscillations of the two fields are perpendicular to each other and perpendicular to the direction of energy and wave propagation, forming a transverse wave. The wavefront of electromagnetic waves emitted from a point source is a sphere. The position of an electromagnetic wave within the electromagnetic spectrum could be characterized by either its frequency of oscillation or its wavelength. The electromagnetic spectrum includes, in order of increasing frequency and decreasing wavelength, radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Electromagnetic waves are produced whenever charged particles are accelerated, and these waves can subsequently interact with other charged particles. M-waves carry energy, momentum, and angular momentum away from their source particle and can impart those quantities to matter with which they interact. Quanta of M-waves are called photons, whose rest mass is zero. Electromagnetic radiation is associated with those M-waves that are free to propagate themselves without the continuing influence of the moving charges that produced them, because they have achieved sufficient distance from those charges. Thus, EMR is sometimes referred to as the far field. In this language, the near field refers to M fields near the charges and current that directly produced them, specifically, electromagnetic induction and electrostatic induction phenomena. Physics. In the quantum theory of electromagnetism, EMR consists of photons, the elementary particles responsible for all electromagnetic interactions. Quantum effects provide additional sources of EMR, such as the transition of electrons to lower energy levels in an atom and black body radiation. The energy of an individual photon is quantized and is greater for photons of higher frequency. This relationship is given by Planck's equation E equals h nu, where E is the energy per photon, nu is the frequency of the photon, and h is Planck's constant. A single gamma-ray photon, for example, might carry 100,000 times the energy of a single photon of visible light. The effects of EMR upon chemical compounds and biological organisms depend both upon the radiation's power and its frequency. EMR of visible or lower frequencies is called non-ionizing radiation, because its photons do not individually have enough energy to ionize atoms or molecules. The effects of these radiations on chemical systems and living tissue are caused primarily by heating effects from the combined energy transfer of many photons. In contrast, high ultraviolet, X-rays and gamma rays are called ionizing radiation, since individual photons of such high frequency have enough energy to ionize molecules or break chemical bonds. These radiations have the ability to cause chemical reactions and damage living cells beyond that resulting from simple heating, and can be a health hazard. Maxwell derived a waveform of the electric and magnetic equations, thus uncovering the wave-like nature of electric and magnetic fields and their symmetry. Because the speed of M waves predicted by the wave equation coincided with the measured speed of light, Maxwell concluded that light itself is an M wave. Maxwell's equations were confirmed by Heinrich Hertz through experiments with radio waves. According to Maxwell's equations, a spatially varying electric field is always associated with a magnetic field that changes over time. Likewise, a spatially varying magnetic field is associated with specific changes over time in the electric field. In an electromagnetic wave, the changes in the electric field are always accompanied by a wave in the magnetic field in one direction, and vice versa. This relationship between the two occurs without either type field causing the other, rather, they occur together in the same way that time and space changes occur together and are interlinked in special relativity. In fact, magnetic fields may be viewed as relativistic distortions of electric fields, so the close relationship between space and time changes here is more than an analogy. Together, these fields form a propagating electromagnetic wave, which moves out into space and need never again affect the source. The distant M field formed in this way by the acceleration of a charge carries energy with it that radiates away through space, hence the term. Maxwell's equations established that some charges and currents produce a local type of electromagnetic field near them that does not have the behavior of EMR. Currents directly produce a magnetic field, but it is of a magnetic dipole type that dies out with distance from the current. In a similar manner, moving charges pushed apart in a conductor by a changing electrical potential produce an electric dipole type electrical field, but this also declines with distance. These fields make up the near field near the EMR source. Neither of these behaviors are responsible for M radiation. Instead, they cause electromagnetic field behavior that only efficiently transfers power to a receiver very close to the source, such as the magnetic induction inside a transformer, or the feedback behavior that happens close to the coil of a metal detector. Typically, near fields have a powerful effect on their own sources, causing an increased load in the source or transmitter, whenever energy is withdrawn from the M field by a receiver. Otherwise, these fields do not propagate freely out into space, carrying their energy away without distance limit, but rather oscillate, returning their energy to the transmitter if it is not received by a receiver. By contrast, the M-far field is composed of radiation that is free of the transmitter in the sense that the transmitter requires the same power to send these changes in the fields out, whether the signal is immediately picked up or not. This distant part of the electromagnetic field is electromagnetic radiation. The far fields propagate without allowing the transmitter to affect them. This causes them to be independent in the sense that their existence and their energy, after they have left the transmitter, is completely independent of both transmitter and receiver. Due to conservation of energy, the amount of power passing through any spherical surface drawn around the source is the same. Because such a surface has an area proportional to the square of its distance from the source, the power density of M radiation always decreases with the inverse square of distance from the source. This is called the inverse square law. This is in contrast to dipole parts of the M field close to the source, which varies in power according to an inverse cube power law, and thus does not transport a conserved amount of energy over distances, but instead fades with distance, with its energy rapidly returning to the transmitter or absorbed by a nearby receiver. The far field depends on a different mechanism for its production than the near field, and upon different terms in Maxwell's equations. Whereas the magnetic part of the near field is due to currents in the source, the magnetic field in EMR is due only to the local change in the electric field. In a similar way, while the electric field in the near field is due directly to the charges and charge separation in the source, the electric field in EMR is due to a change in the local magnetic field. Both processes for producing electric and magnetic EMR fields have a different dependence on distance than do near-field dipole electric and magnetic fields. That is why the EMR type of M field becomes dominant in power far from sources. The term far from sources refers to how far from the source any portion of the outward moving M field is located, by the time that source currents are changed by the varying source potential, and the source has therefore begun to generate an outwardly moving M field of a different phase. A more compact view of EMR is that the far field that composes EMR is generally that part of the M field that has traveled sufficient distance from the source, that it has become completely disconnected from any feedback to the charges and currents that were originally responsible for it. Now independent of the source charges, the M field, as it moves farther away, is dependent only upon the accelerations of the charges that produced it. It no longer has a strong connection to the direct fields of the charges, or to the velocity of the charges. In the Leonard-Weichert potential formulation of the electric and magnetic fields due to motion of a single particle, the terms associated with acceleration of the particle are those that are responsible for the part of the field that is regarded as electromagnetic radiation. By contrast, the term associated with the changing static electric field of the particle and the magnetic term that results from the particle's uniform velocity, are both associated with the electromagnetic near field, and do not comprise M radiation. Theory. Electrodynamics is the physics of electromagnetic radiation, and electromagnetism is the physical phenomenon associated with the theory of electrodynamics. Electric and magnetic fields obey the properties of superposition. Thus, a field due to any particular particle or time-varying electric or magnetic field contributes to the fields present in the same space due to other causes. Further, as they are vector fields, all magnetic and electric field vectors add together according to vector addition. For example, in optics two or more coherent light waves may interact and by constructive or destructive interference yield a resultant irradiance deviating from the sum of the component irradiances of the individual light waves. Since light is an oscillation, it is not affected by traveling through static electric or magnetic fields in a linear medium such as a vacuum. However, in nonlinear media, such as some crystals, interactions can occur between light and static electric and magnetic fields. These interactions include the Faraday effect and the Kerr effect. In refraction, a wave crossing from one medium to another of different density alters its speed and direction upon entering the new medium. The ratio of the refractive indices of the media determines the degree of refraction, and is summarized by Snell's law. Light of composite wavelengths disperses into a visible spectrum passing through a prism, because of the wavelength-dependent refractive index of the prism material, that is, each component wave within the composite light is bent a different amount. M radiation exhibits both wave properties and particle properties at the same time. Both wave and particle characteristics have been confirmed in many experiments. Wave characteristics are more apparent when M radiation is measured over relatively large timescales and over large distances, while particle characteristics are more evident when measuring small timescales and distances. For example, when electromagnetic radiation is absorbed by matter, particle-like properties will be more obvious when the average number of photons in the cube of the relevant wavelength is much smaller than 1. It is not too difficult to experimentally observe non-uniform deposition of energy when light is absorbed, however this alone is not evidence of particulate behavior. Rather, it reflects the quantum nature of matter. demonstrating that the light itself is quantized, not merely its interaction with matter, is a more subtle affair. Some experiments display both the wave and particle natures of electromagnetic waves, such as the self-interference of a single photon. When a single photon is sent through an interferometer, it passes through both paths, interfering with itself, as waves do, yet is detected by a photomultiplier or other sensitive detector only once. A quantum theory of the interaction between electromagnetic radiation and matter such as electrons is described by the theory of quantum electrodynamics. Electromagnetic waves can be polarized, reflected, refracted, diffracted or interfere with each other. Maxwell's equations. Near and far fields. Electromagnetic radiation is a transverse wave, meaning that its oscillations are perpendicular to the direction of energy transfer and travel. The electric and magnetic parts of the field stand in a fixed ratio of strengths in order to satisfy the two Maxwell equations that specify how one is produced from the other. These E and B fields are also in phase, with both reaching maxima and minima at the same points in space. A common misconception is that the E and B fields in electromagnetic radiation are out of phase because a change in one produces the other, and this would produce a phase difference between them as sinusoidal functions. However, in the far-field M radiation, which is described by the two source-free Maxwell-Curl operator equations, a more correct description is that a time change in one type of field is proportional to a space change in the other. These derivatives require that the E and B fields in EMR are in phase. Properties. Wave model, particle model and quantum theory. Wave-particle duality. Wave and particle effects of electromagnetic radiation. An important aspect of light's nature is its frequency. The frequency of a wave is its rate of oscillation and is measured in Hertz, the SI unit of frequency, where 1 Hz is equal to 1 oscillation per second. Light usually has multiple frequencies that sum to form the resultant wave. Different frequencies undergo different angles of refraction, a phenomenon known as dispersion. A wave consists of successive troughs and crests, and the distance between two adjacent crests or troughs is called the wavelength. Waves of the electromagnetic spectrum vary in size, from very long radio waves the size of buildings to very short gamma rays smaller than atom nuclei. Frequency is inversely proportional to wavelength, according to the equation, where v is the speed of the wave, f is the frequency and lambda is the wavelength. As waves cross boundaries between different media, their speeds change but their frequencies remain constant. Propagation speed. Electromagnetic waves in free space must be solutions of Maxwell's electromagnetic wave equation. Two main classes of solutions are known, namely plane waves and spherical waves. The plane waves may be viewed as the limiting case of spherical waves at a very large distance from the source. Both types of waves can have a waveform which is an arbitrary time function. As with any time function, this can be decomposed by means of Fourier analysis into its frequency spectrum, or individual sinusoidal components, each of which contains a single frequency, amplitude, and phase. Such a component wave is said to be monochromatic. A monochromatic electromagnetic wave can be characterized by its frequency or wavelength, its peak amplitude, its phase relative to some reference phase, its direction of propagation and its polarization. Interference is the superposition of two or more waves resulting in a new wave pattern. If the fields have components in the same direction, they constructively interfere, while opposite directions cause destructive interference. An example of interference caused by EMR is electromagnetic interference, or as it is more commonly known as, radio frequency interference. Additionally, multiple polarization signals can be combined to form new states of polarization, which is known as parallel polarization state generation. The energy in electromagnetic waves is sometimes called radiant energy. An anomaly arose in the late 19th century involving a contradiction between the wave theory of light and measurements of the electromagnetic spectra that were being emitted by thermal radiators known as black bodies. Physicists struggled with this problem, which later became known as the ultraviolet catastrophe, unsuccessfully for many years. In 1900, Max Planck developed a new theory of black body radiation that explained the observed spectrum. Planck's theory was based on the idea that black bodies emit light only as discrete bundles or packets of energy. These packets were called quanta. Later, Albert Einstein proposed that light quanta be regarded as real particles. Later, the particle of light was given the name photon, to correspond with other particles being described around this time, such as the electron and proton. A photon has an energy, E, proportional to its frequency, F, by where h is Planck's constant, lambda, is the wavelength and c is the speed of light. This is sometimes known as the Planck-Einstein equation. In quantum theory, the energy of the photons is thus directly proportional to the frequency of the EMR wave. Likewise, the momentum p of a photon is also proportional to its frequency and inversely proportional to its wavelength. The source of Einstein's proposal that light was composed of particles was an experimental anomaly not explained by the wave theory, the photoelectric effect, in which light striking a metal surface ejected electrons from the surface, causing an electric current to flow across an applied voltage. Experimental measurements demonstrated that the energy of individual ejected electrons was proportional to the frequency, rather than the intensity, of the light. Furthermore, below a certain minimum frequency, which depended on the particular metal, no current would flow regardless of the intensity. These observations appeared to contradict the wave theory, and for years physicists tried in vain to find an explanation. In 1905, Einstein explained this puzzle by resurrecting the particle theory of light to explain the observed effect. Because of the preponderance of evidence in favor of the wave theory, however, Einstein's ideas were met initially with great skepticism among established physicists. Eventually, Einstein's explanation was accepted as new particle-like behavior of light was observed, such as the Compton effect. Special theory of relativity. As a photon is absorbed by an atom, it excites the atom, elevating an electron to a higher energy level. When an electron in an excited molecule or atom descends to a lower energy level, it emits a photon of light at a frequency corresponding to the energy difference. Since the energy levels of electrons in atoms are discrete, each element and each molecule emits and absorbs its own characteristic frequencies. Immediate photon emission is called fluorescence, a type of photoluminescence. An example is visible light emitted from fluorescent paints, in response to ultraviolet. Many other fluorescent emissions are known in spectral bands other than visible light. Delayed emission is called phosphorescence. The modern theory that explains the nature of light includes the notion of wave-particle duality. More generally, the theory states that everything has both a particle nature and a wave nature, and various experiments can be done to bring out one or the other. The particle nature is more easily discerned using an object with a large mass. A bold proposition by Louis de Broglie in 1924 led the scientific community to realize that electrons also exhibited wave-particle duality. History of discovery. Together, wave and particle effects fully explain the emission and absorption spectra of M radiation. The matter composition of the medium through which the light travels determines the nature of the absorption and emission spectrum. These bands correspond to the allowed energy levels in the atoms. Dark bands in the absorption spectrum are due to the atoms in an intervening medium between source and observer. The atoms absorb certain frequencies of the light between emitter and detector/I, then emit them in all directions. A dark band appears to the detector, due to the radiation scattered out of the beam. For instance, dark bands in the light emitted by a distant star are due to the atoms in the star's atmosphere. A similar phenomenon occurs for emission, which is seen when an emitting gas glows due to excitation of the atoms from any mechanism, including heat. As electrons descend to lower energy levels, a spectrum is emitted that represents the jumps between the energy levels of the electrons, but lines are seen because again emission happens only at particular energies after excitation. An example is the emission spectrum of nebulae. Rapidly moving electrons are most sharply accelerated when they encounter a region of force, so they are responsible for producing much of the highest frequency electromagnetic radiation observed in nature. These phenomena can aid various chemical determinations for the composition of gases lit from behind and for glowing gases. Spectroscopy determines what chemical elements comprise a particular star. Spectroscopy is also used in the determination of the distance of a star, using the red shift. Electromagnetic spectrum. Interactions as a function of frequency. Radio and microwave. Any electric charge that accelerates, or any changing magnetic field, produces electromagnetic radiation. Electromagnetic information about the charge travels at the speed of light. Accurate treatment thus incorporates a concept known as retarded time, which adds to the expressions for the electrodynamic electric field and magnetic field. These extra terms are responsible for electromagnetic radiation. When any wire conducts alternating current, electromagnetic radiation is propagated at the same frequency as the current. In many such situations it is possible to identify an electrical dipole moment that arises from separation of charges due to the exciting electrical potential, and this dipole moment oscillates in time, as the charges move back and forth. This oscillation at a given frequency gives rise to changing electric and magnetic fields, which then set the electromagnetic radiation in motion. At the quantum level, electromagnetic radiation is produced when the wave packet of a charged particle oscillates or otherwise accelerates. Charged particles in a stationary state do not move, but a superposition of such states may result in a transition state that has an electric dipole moment that oscillates in time. This oscillating dipole moment is responsible for the phenomenon of radiative transition between quantum states of a charged particle. Such states occur in atoms when photons are radiated as the atom shifts from one stationary state to another. As a wave, light is characterized by a velocity, wavelength, and frequency. As particles, light is a stream of photons. Each has an energy related to the frequency of the wave given by Planck's relation E equals hf, where E is the energy of the photon, h equals 6.626 times 1034 Js is Planck's constant, and f is the frequency of the wave. One rule is obeyed regardless of circumstances: radiation in a vacuum travels at the speed of light, relative to the observer, regardless of the observer's velocity. In a medium, velocity factor or refractive index are considered, depending on frequency and application. Both of these are ratios of the speed in a medium to speed in a vacuum. By the late 19th century, various experimental anomalies could not be explained by the simple wave theory. One of these anomalies involved a controversy over the speed of light. The speed of light and other EMR predicted by Maxwell's equations did not appear unless the equations were modified in a way first suggested by Fitzgerald and Lorentz, or else otherwise that speed would depend on the speed of observer relative to the medium which supposedly carried the electromagnetic wave. Experiments failed to find any observer effect. In 1905, Einstein proposed that space and time appeared to be velocity-changeable entities for light propagation and all other processes and laws. These changes accounted for the constancy of the speed of light and all electromagnetic radiation, from the viewpoints of all observers, even those in relative motion. Electromagnetic radiation of wavelengths other than those of visible light were discovered in the early 19th century. The discovery of infrared radiation is ascribed to astronomer William Herschel, who published his results in 1800 before the Royal Society of London. Herschel used a glass prism to refract light from the sun and detected invisible rays that caused heating beyond the red part of the spectrum, through an increase in the temperature recorded with a thermometer. These calorific rays were later termed infrared. In 1801, German physicist Johann Wilhelm Ritter discovered ultraviolet in an experiment similar to Herschel's, using sunlight and a glass prism. Ritter noted that invisible rays near the violet edge of a solar spectrum dispersed by a triangular prism darkened silver chloride preparations more quickly than did the nearby violet light. Ritter's experiments were an early precursor to what would become photography. Ritter noted that the ultraviolet rays were capable of causing chemical reactions. In 1862-4, James Clerk Maxwell developed equations for the electromagnetic field which suggested that waves in the field would travel with a speed that was very close to the known speed of light. Maxwell therefore suggested that visible light all consisted of propagating disturbances in the electromagnetic field. Radio waves were first produced deliberately by Heinrich Hertz in 1887, using electrical circuits calculated to produce oscillations at a much lower frequency than that of visible light, following recipes for producing oscillating charges and currents suggested by Maxwell's equations. Hertz also developed ways to detect these waves, and produced and characterized what were later termed radio waves and microwaves. 286,7. Wilhelm Röntgen discovered and named X-rays. After experimenting with high voltages applied to an evacuated tube on November 8, 1895, he noticed a fluorescence on a nearby plate of coated glass. In 1 month, he discovered X-rays' main properties, 307. The last portion of the M spectrum to be discovered was associated with radioactivity. Henri Becquerel found that uranium salts caused fogging of an unexposed photographic plate through a covering paper in a manner similar to X-rays, and Marie Curie discovered that only certain elements gave off these rays of energy, soon discovering the intense radiation of radium. The radiation from pitchblende was differentiated into alpha rays and beta rays by Ernest Rutherford through simple experimentation in 1899, but these proved to be charged particulate types of radiation. However, in 1900 the French scientist Paul Villard discovered a third neutrally charged and especially penetrating type of radiation from radium, and after he described it, Rutherford realized it must be yet a third type of radiation, which in 1903 Rutherford named gamma rays. In 1910 British physicist William Henry Bragg demonstrated that gamma rays are electromagnetic radiation, not particles, and in 1914 Rutherford and Edward Andrade measured their wavelengths, finding that they were similar to X-rays but with shorter wavelengths and higher frequency, although a crossover between X and gamma rays makes it possible to have X-rays with a higher energy than gamma rays and vice versa. The origin of the ray differentiates them. Gamma rays tend to be a natural phenomena originating from the unstable nucleus of an atom, and X-rays are electrically generated unless they are as a result of Bremsstrahlung X radiation caused by the interaction of fast-moving particles colliding with certain materials, usually of higher atomic numbers, 308,9. M radiation is classified by wavelength into radio, microwave, infrared, visible, ultraviolet, X-rays and gamma rays. Arbitrary electromagnetic waves can be expressed by Fourier analysis in terms of sinusoidal monochromatic waves, which in turn can each be classified into these regions of the EMR spectrum. For certain classes of M waves, the waveform is most usefully treated as random, and then spectral analysis must be done by slightly different mathematical techniques appropriate to random or stochastic processes. In such cases, the individual frequency components are represented in terms of their power content, and the phase information is not preserved. Such a representation is called the power spectral density of the random process. Random electromagnetic radiation requiring this kind of analysis is, for example, encountered in the interior of stars, and in certain other very wideband forms of radiation such as the zero-point wave field of the electromagnetic vacuum. The behavior of M radiation depends on its frequency. Lower frequencies have longer wavelengths, and higher frequencies have shorter wavelengths, and are associated with photons of higher energy. There is no fundamental limit known to these wavelengths or energies, at either end of the spectrum, although photons with energies near the Planck energy or exceeding it will require new physical theories to describe. Sound waves are not electromagnetic radiation. At the lower end of the electromagnetic spectrum, about 20 Hz to about 20 kHz, are frequencies that might be considered in the audio range. However, electromagnetic waves cannot be directly perceived by human ears. Sound waves are instead the oscillating compression of molecules. To be heard, electromagnetic radiation must be converted to pressure waves of the fluid in which the ear is located. When M radiation interacts with matter, its behavior changes qualitatively as its frequency changes. At radio and microwave frequencies, EMR interacts with matter largely as a bulk collection of charges which are spread out over large numbers of affected atoms. In electrical conductors, such induced bulk movement of charges results in absorption of the EMR, or else separations of charges that cause generation of new EMR. An example is absorption or emission of radio waves by antennas, or absorption of microwaves by water or other molecules with an electric dipole moment, as for example inside a microwave oven. These interactions produce either electric currents or heat, or both. Like radio and microwave, infrared also is reflected by metals. However, unlike lower frequency radio and microwave radiation, infrared EMR commonly interacts with dipoles present in single molecules, which change as atoms vibrate at the ends of a single chemical bond. It is consequently absorbed by a wide range of substances, causing them to increase in temperature as the vibrations dissipate as heat. The same process, run in reverse, causes bulk substances to radiate in the infrared spontaneously. As frequency increases into the visible range, photons have enough energy to change the bond structure of some individual molecules. It is not a coincidence that this happens in the visible range, as the mechanism of vision involves the change in bonding of a single molecule which absorbs light in the rhodopsin in the retina of the human eye. Photosynthesis becomes possible in this range as well, for similar reasons, as a single molecule of chlorophyll is excited by a single photon. Animals that detect infrared make use of small packets of water that change temperature, in an essentially thermal process that involves many photons. For this reason, infrared, microwaves and radio waves are thought to damage molecules in biological tissue only by bulk heating, not excitation from single photons of the radiation. Visible light is able to affect a few molecules with single photons, but usually not in a permanent or damaging way, in the absence of power high enough to increase temperature to damaging levels. However, in plant tissues that conduct photosynthesis, carotenoids act to quench electronically excited chlorophyll produced by visible light in a process called non-photochemical quenching, in order to prevent reactions that would otherwise interfere with photosynthesis at high light levels. Limited evidence indicate that some reactive oxygen species are created by visible light in skin, and that these may have some role in photoaging, in the same manner as ultraviolet A. As frequency increases into the ultraviolet, photons now carry enough energy to excite certain doubly bonded molecules into permanent chemical rearrangement. In DNA, this causes lasting damage. DNA is also indirectly damaged by reactive oxygen species produced by ultraviolet A, which has energy too low to damage DNA directly. This is why ultraviolet at all wavelengths can damage DNA, and is capable of causing cancer, and skin burns that are far worse than would be produced by simple heating effects. This property of causing molecular damage that is out of proportion to heating effects, is characteristic of all EMR with frequencies at the visible light range and above. These properties of high-frequency EMR are due to quantum effects that permanently damage materials and tissues at the molecular level. At the higher end of the ultraviolet range, the energy of photons becomes large enough to impart enough energy to electrons to cause them to be liberated from the atom, in a process called photoionization. The energy required for this is always larger than about 10 electron volts, corresponding with wavelengths smaller than 124 nm. This high end of the ultraviolet spectrum with energies in the approximate ionization range is sometimes called extreme UV. Ionizing UV is strongly filtered by the Earth's atmosphere. Electromagnetic radiation composed of photons that carry minimum ionization energy, or more, is therefore termed ionizing radiation. Electromagnetic type ionizing radiation extends from the extreme ultraviolet to all higher frequencies and shorter wavelengths, which means that all X-rays and gamma rays qualify. These are capable of the most severe types of molecular damage, which can happen in biology to any type of biomolecule, including mutation and cancer, and often at great depths below the skin, since the higher end of the X-ray spectrum, and all of the gamma-ray spectrum, penetrate matter. Most UV and X-rays are blocked by absorption first from molecular nitrogen, and then from the electronic excitation of dioxygen and finally ozone at the mid-range of UV. Only 30% of the sun's ultraviolet light reaches the ground, and almost all of this is well transmitted. Visible light is well transmitted in air, as it is not energetic enough to excite nitrogen, oxygen, or ozone, but too energetic to excite molecular vibrational frequencies of water vapor. Absorption bands in the infrared are due to modes of vibrational excitation in water vapor. However, at energies too low to excite water vapor, the atmosphere becomes transparent again, allowing free transmission of most microwave and radio waves. Finally, at radio wavelengths longer than 10 meters or so, the air in the lower atmosphere remains transparent to radio, but plasma in certain layers of the ionosphere begins to interact with radio waves. This property allows some longer wavelengths to be reflected and results in shortwave radio beyond line of sight. However, certain ionospheric effects begin to block incoming radio waves from space, when their frequency is less than about 10 MHz. Radio waves have the least amount of energy and the lowest frequency. When radio waves impinge upon a conductor, they couple to the conductor, travel along it and induce an electric current on the conductor surface by moving the electrons of the conducting material in correlated bunches of charge. Such effects can cover macroscopic distances in conductors, since the wavelength of radio waves is long. Microwaves are a form of electromagnetic radiation with wavelengths ranging from as long as 1 meter to as short as 1 millimeter, with frequencies between 300 MHz and 300 GHz. Natural sources produce M radiation across the spectrum. M radiation with a wavelength between approximately 400 nm and 700 nm is directly detected by the human eye and perceived as visible light. Other wavelengths, especially nearby infrared and ultraviolet, are also sometimes referred to as light. The basic structure of matter involves charged particles bound together. When electromagnetic radiation impinges on matter, it causes the charged particles to oscillate and gain energy. The ultimate fate of this energy depends on the context. It could be immediately re-radiated and appear as scattered, reflected, or transmitted radiation. It may get dissipated into other microscopic motions within the matter, coming to thermal equilibrium and manifesting itself as thermal energy, or even kinetic energy, in the material. With a few exceptions related to high-energy photons, absorbed electromagnetic radiation simply deposits its energy by heating the material. This happens for infrared, microwave and radio wave radiation. Intense radio waves can thermally burn living tissue and can cook food. In addition to infrared lasers, sufficiently intense visible and ultraviolet lasers can easily set paper afire. Ionizing radiation creates high-speed electrons in a material and breaks chemical bonds, but after these electrons collide many times with other atoms, eventually most of the energy becomes thermal energy, all in a tiny fraction of a second. This process makes ionizing radiation far more dangerous per unit of energy than non-ionizing radiation. This caveat also applies to UV, even though almost all of it is not ionizing, because UV can damage molecules due to electronic excitation, which is far greater per unit energy than heating effects. Infrared radiation in the spectral distribution of a black body is usually considered a form of heat, since it has an equivalent temperature and is associated with an entropy change per unit of thermal energy. However, heat is a technical term in physics and thermodynamics and is often confused with thermal energy. Any type of electromagnetic energy can be transformed into thermal energy in interaction with matter. Thus, any electromagnetic radiation can heat a material, when it is absorbed. The inverse or time-reversed process of absorption is thermal radiation. Much of the thermal energy in matter consists of random motion of charged particles, and this energy can be radiated away from the matter. The resulting radiation may subsequently be absorbed by another piece of matter, with the deposited energy heating the material. The electromagnetic radiation in an opaque cavity at thermal equilibrium is effectively a form of thermal energy, having maximum radiation entropy. Bioelectromagnetics is the study of the interactions and effects of radiation on living organisms. The effects of electromagnetic radiation upon living cells, including those in humans, depends upon the radiation's power and frequency. For low-frequency radiation, the best understood effects are those due to radiation power alone, acting through heating when radiation is absorbed. For these thermal effects, frequency is important only as it affects penetration into the organism. It is widely accepted that low-frequency fields that are too weak to cause significant heating could not possibly have any biological effect. Despite the commonly accepted results, some research has been conducted to show that weaker non-thermal electromagnetic fields, and modulated RF and microwave fields have biological effects. Fundamental mechanisms of the interaction between biological material and electromagnetic fields at non-thermal levels are not fully understood. Infrared. The World Health Organization has classified radio frequency electromagnetic radiation as Group 2B, possibly carcinogenic. This group contains possible carcinogens such as lead, DDT, and styrene. For example, epidemiological studies looking for a relationship between cell phone use and brain cancer development have been largely inconclusive, save to demonstrate that the effect, if it exists, cannot be a large one. At higher frequencies, the effects of individual photons begin to become important, as these now have enough energy individually to directly or indirectly damage biological molecules. All UV frequencies have been classed as Group 1 carcinogens by the World Health Organization. Ultraviolet radiation from sun exposure is the primary cause of skin cancer. Thus, at UV frequencies and higher, electromagnetic radiation does more damage to biological systems than simple heating predicts. This is most obvious in the far ultraviolet. UV, with X-ray and gamma radiation, are referred to as ionizing radiation due to the ability of photons of this radiation to produce ions and free radicals in materials. Since such radiation can severely damage life at energy levels that produce little heating, it is considered far more dangerous than the rest of the electromagnetic spectrum. Electromagnetic waves were predicted by the classical laws of electricity and magnetism, known as Maxwell's equations. Inspection of Maxwell's equations without sources results in non-trivial solutions of changing electric and magnetic fields. Beginning with Maxwell's equations in free space equals I x plus j y plus k z plus plus. Visible light. One solution is trivial. Ultraviolet. For a more useful solution, we utilize vector identities, which work for any vector, as follows. The curl of equation. X-rays and gamma rays. Atmosphere and magnetosphere. Evaluating the left-hand side. Evaluating the right-hand side. Equations n are equal, so this results in a vector-valued differential equation for the electric field, namely types and sources, classed by spectral band. Radio waves, microwaves, infrared 2, visible light 2, ultraviolet 2, X-rays, gamma rays, thermal radiation and electromagnetic radiation as a form of heat. Biological effects. Derivation from electromagnetic theory. Applying a similar pattern results in similar differential equation for the magnetic field. These differential equations are equivalent to the wave equation. Or more simply, in the case of the electric and magnetic fields, the speed is. This is the speed of light in vacuum. Maxwell's equations unified the vacuum permittivity, 0, the vacuum permeability, μ, 0, and the speed of light itself, c0. This relationship had been discovered by Wilhelm Eduard Weber and Rudolf Kohlrausch prior to the development of Maxwell's electrodynamics. However, Maxwell was the first to produce a field theory consistent with waves traveling at the speed of light. These are only two equations versus the original four, so more information pertains to these waves hidden within Maxwell's equations. A generic vector wave for the electric field. Here, E0 is the constant amplitude, f is any second differentiable function, k is a unit vector in the direction of propagation, and x is a position vector, f, k, x, c, 0, t is a generic solution to the wave equation. In other words, for a generic wave traveling in the k direction, this form will satisfy the wave equation. The first of Maxwell's equations implies that the electric field is orthogonal to the direction the wave propagates. The second of Maxwell's equations yields the magnetic field. The remaining equations will be satisfied by this choice of E, B, \math. The electric and magnetic field waves in the far field travel at the speed of light. They have a special restricted orientation and proportional magnitudes, E, 0, equals, C, 0, B, 0, equals CB, which can be seen immediately from the pointing vector. The electric field, magnetic field, and direction of wave propagation are all orthogonal, and the wave propagates in the same direction as E times B \math. Also, E and B far fields in free space, which as wave solutions depend primarily on these two Maxwell equations, are in phase with each other. This is guaranteed since the generic wave solution is first order in both space and time, and the curl operator on one side of these equations results in first-order spatial derivatives of the wave solution, while the time derivative on the other side of the equations, which gives the other field, is first order in time, resulting in the same phase shift for both fields in each mathematical operation. From the viewpoint of an electromagnetic wave traveling forward, the electric field might be oscillating up and down, while the magnetic field oscillates right and left. This picture can be rotated with the electric field oscillating right and left and the magnetic field oscillating down and up. This is a different solution that is traveling in the same direction. This arbitrariness in the orientation with respect to propagation direction is known as polarization. On a quantum level, it is described as photon polarization. The direction of the polarization is defined as the direction of the electric field. More general forms of the second-order wave equations given above are available, allowing for both non-vacuum propagation media and sources. Many competing derivations exist, all with varying levels of approximation and intended applications. One very general example is a form of the electric field equation, which was factorized into a pair of explicitly directional wave equations, and then efficiently reduced into a single unidirectional wave equation by means of a simple slow evolution approximation.